Shall we get started? So you probably already know that if we have a function f of x, let's call this a, this is b, and if we integrate f of x from a to b with respect to x, that will give us the area between the curve and the x-axis, right? That's just the definition of integral. You saw this already, I suppose. But before we go into that, so this gives this area. That's just something to keep in mind whenever you think about integrals. Right. Before we do that, let's talk about a few properties with definite integrals from 5.2. So the first one is that if you integrate a function, a continuous function f of x with respect to x from a to a, basically from a point to itself, that is always going to be a 0, because if you think about it, if we only integrate this function f from a to itself, there's really no area between them. Right, so the integral should be 0. And then the second one is that if you integrate it from a to b of f of x dx, that's the same thing as integrating as a negative value of integrating from b to a f of x dx. So if you flip the lower and the upper bound, the value becomes the opposite. And if you're integrating from a to b of a constant c times some function f of x dx, that constant doesn't get involved in the integration process, so you can put it out in front of the integral. That becomes c multiplied by the integral of a to b f of x dx. This rule is very useful a lot of times if you have a strange, like a weird constant, like a square root of pi or something. You can always move it to the front, leave it alone. The next one is if you're integrating from a to b of two functions, f of x, adding g of x, or sometimes minus g of x with respect to x, that means you can integrate each function separately and then just add up the integrals at the end. So one more forgetting. Oh yeah, if you're integrating a to b of 1 dx, it's just 1. Usually we don't even write the 1 there, just integrating from a to b of dx. That's just going to be b minus a. We're going to talk about that more later. But this is coming from if you're integrating just infinite integral from just no boundaries of dx, that's just going to be x. You should remember that. And last one, if we say you have a and a b, and in the middle we have a c, it's just kind of like an area. We can divide it into two parts and add up the two areas together to get the total area. It's the same thing with integrals. If we have a c between a and a b, if we're integrating from a to b f of x dx, we can integrate from a to c first to get the area on the left, f of x dx. Then we're going to add the area on the right, which is from c to b f of x dx. So we're basically splitting the interval from A to B into A to C and a C to B. So those are the properties of definite integral. It's from the book 5.2. Any questions on those? I would say the one that you're probably going to use a lot more is probably the second one. When you flip the lower and the upper bound, that one you're going to see a bit more. And then when you have a constant, you're going to see that. But obviously, if you're adding and subtracting two functions, that's just always there. Those three you're probably going to see a little bit more. Where does C come from? C, so there's a few questions. Well, let me answer the last one. So where does C come from? C is just a point I picked, a random point I picked between A and B. In the drawing I have. So I'm basically splitting the area between A and B into two small areas, between A and C and the C and B. That's what C does. There's a couple other questions. Let's see. So there was a question earlier about what was the policy on calculator use. Generally speaking, using a calculator is fine if you just need a calculator to calculate some numerical answers. That's totally fine. But you are not allowed to use notes on quizzes and exams. That's right. You also cannot use internet. I know that there's a lot of websites and apps that you can basically take a picture or put it in the problem and they're going to solve it for you. That is absolutely not allowed. Also, you cannot use your textbook when you take quizzes and exams. It's just do your best, learn the material and try to do your best on those assessments, right? It's assessments are supposed to help you kind of like gain a deep understanding with the material, and also for you to find out how much you really understand the topics. It's not for me to punish you or, try to hurt you with a bad grade. So just do your best. Oh, by the way, I forgot to say that. 6 quizzes, the lowest will be dropped at the end when we calculate the total grades. All right, so those are the properties. I'm going to give you an example to use them. So here's the example. I'm going to make sure the notes are available on the website later, but you probably don't have time to write this down. That's okay. Just do your best. So here's the function g of x. That's the curve in purple. It's a continuous function, and it has 3 parts. So the first part is given by this h1 of x. And the middle part, we're going to call it h2 of x, and then the last part, we're going to call it h3. So this is 2, this is 6, 7. Right, so those the hg of x, it's a piecewise function of 3 parts. And then we know that from 0 to 2, if we integrate that function h1, we get 4. From 2 to 6, if we integrate h2, we get -2 pi. And from 6 to 7, if we integrate the last piece of the function, we get 1/2. I want to point out that the reason we get -2 pi in the middle here, it's because it's that area. That's because this area is below the x-axis. Any area below x-axis is always a negative area. The area above it is a positive area. Those two are positive values, but the middle part is a negative area because it's below the x-axis. So the first part says, if we want to integrate from 3 to 3 of the g of x, so that will give us an area from 3 to 3 of this g of x function, what do you suppose the area is? 0. Excellent. So that is 0. You don't even have to think too much because the lower bound and the upper bound, they're together, right? So basically the area doesn't cover anything. Sorry, you cannot see me. So the curve, the area we're looking for is from 3 to 3. So it's basically we're looking at the area of a vertical line. There's no area. So that's 0. So the second one says we want to integrate from 6 to 2 of g of x. Well, we're basically looking from 6 to 2, this part, for the area between the function and the x-axis. Again, we're looking for this area, but that's not exactly the area given, because the one we given is from 2 to 6. So we have to flip the boundaries. So integral from 6 to 2 is a negative integral from 2 to 6. When we flip the boundaries, we add the opposite sign of g of x dx. Oh, I should have dx in all of them. Too quickly, I forgot about it. And then that is just going to be from 2 to 6. The g function is exactly the h of 2 function. So h of 2 of x dx. And then this part we already know because it's given. That's negative 2 pi. So we get negative of negative 2 pi, 2 pi. So the second example is just basically practice the property of flipping the lower and the upper bound to get the opposite sign. Anyone know what the third one will give me if I integrate the g function from 0 to 2 of 5 of g of x? Exactly. Excellent. So yeah, so the 5, like I said earlier, it's a constant coefficient. You can just move it in front of the integral notation. So that's a 5 integrating 0 to 2 of g of x dx. But the g of x function is the same as h1 of x function. So we can substitute for that. So that's a 5 integral from 0 to 2 h1 of x dx. This part we know it's given. That's just 2. That's a 4. 5 times 4. We can figure out what the number is. The last part is that we want to integrate g of x from 2 to 7. What do we do? Because all the integrals that we were given, none of them says it's from 2 to 7 or 7 to 2. Split the bounds exactly. So what we do is that we're going to split the integral. So the g of x from 2 to 7 actually is made of 2 functions, right? h2 and h3. So we can split the integral into from 2 to 6. That's the first function, h of 2 x dx. And then the second part of the area is given by from 6 to 7. That's given by h of 3 function. And we can find out the area for each part. The first part is negative 2 pi. The last part is 1/2. Feel free to leave your answer like that. If you see something similar, if you have some answers with pi or e on future assessments, you can also put in the calculator if you want, but that's not necessary. Any questions about those? So that's just a quick review. The next thing I'm going to talk about is called fundamental theorems of calculus, which is 5.3. There are 2 of them. So the first one says, How do we know when to use H1, H2, H3? That's a good question. In this particular example I'm giving, so the curve from 0 to 7, that function altogether has 3 pieces. We're going to call it g of x. You just have to know which interval you talk about. If we talk about g of x, say from 0 to 2, that in the from 0 to 2, that interval there, that part, the g of x is given by h1 of x. So that's when we know we're going to use h1. But if we're looking for intervals from, let's say 6 to 7 of g of x, in this interval, g of x is the same thing as h3, so we're going to use h3 in that part. So again, it depends on which interval you're looking at. That's how you know which function to use. Good question. Will we always be given the area of integral? In this type of questions, yes, it will be given. But after today's 5.3, you will be able to calculate the area on your own by using fundamental theorem of calculus 2. All right. Any other questions? Not hearing any questions, so I'm gonna do. Oh, 2 pi, right, number 2. Like I said, I'll make sure this notes are available to you later on the on-Canvas page. All right. So fundamental theorem of calculus first part, we're going to write FTC1. It says, I'm just going to copy from the book. It's on page 400 in the book. So it says, if f is a continuous function, if f is continuous, on integral a to b, then the function g of x defined as g of x is equal to the integral of a to x of f of t dt with a less than or equal to x less than or equal to b. So basically, it's like the same diagram we have. So if you have f here, this is a, this is b, and this is x is somewhere in the middle. We're going to call it x, just like the c we picked, but in this case we use x. X could be any number between a and b. So if we define g of x from 0 to x, sorry, from a to x, f of t dt, basically g of x is the area function between the area between the curve and the x-axis from a to x. So that's what g is. So this curve here is f of, you can call it f of t or f of x. And then this part, this is g of x, the area, the green part. So if we define g as this integral function, then we can see that g is continuous on a to b, and also g is differentiable open interval a to b, and more importantly, the derivative of g. So if we take the derivative of the area function, will be equal to f of x. So this is the important part. So we usually use this first part of the theorem to find out the derivative of some integral function. There's a few examples. I'm going to go through them with you. Hopefully that will make a bit more sense. So that's how that. So if we have g of x is defined like this, based on f, then we can find the derivative of g, which is equivalent to f of x. That's a proof in the book. We're not going through them. Is f of t equal to f of x? In this notation, then they're not the same because of the independent variable they have. The f of t depends on t, but f of x depends on x, so they're really not the same function. But if you assuming x and the t are the same, they're really the same function. Good question. So f of x and f of t are same if we have x equals t. But if we don't have that, then they're not the same. Good question. All right, so let me go through a couple examples with you. Hopefully that will make it a little bit easier to apply this theorem. All right. The first example here is that, so if we have y is defined as from of integral from a to x of square root t cubed plus 1 dt, where x is between a and a b. And then we want to know the derivative of this function. So this function, we call it y. So we want to know, so we want derivative of y. So dy dx. That's what we're looking for. Or y prime. Am I moving too fast? I feel like probably talking, some of you need to write down the problems. I'll pause for a minute. Yes, Philip, those will be posted on Canvas page. In the future, if I use worksheets like this, I'll probably, I'll try to remember to make them available on Canvas also before the lecture, so you don't have to spend too much time writing down the questions. Okay, so how do we find the derivative? Well, to find the derivative here, so we want to find the derivative, so y prime equals dy dt, sorry, dy dx. So that's equal to d dx of this function, integral from a to x with square root t cubed plus 1 dt. That's what we're looking for, right? We're looking for the derivative. But if you go back, if we call this g of x, then the derivative of g is just going to equal to f of x based on the theorem we had earlier, right? So that's what this part tells us. But the first thing we need to make sure that the square root of t cubed plus 1 is continuous from a to x. In this case, it is. So since square root of t cubed plus 1 is continuous on a and b, then we can apply the fundamental theorem of calculus first part, which says g prime of x equals f of x. Right? So we're just going to apply that directly. So this derivative, kind of like the derivative of g prime, that is equal to the f function with x in it. So the f function is, this is the f function given. So it's just going to be square root, instead of t cubed will be x cubed plus 1. That's the derivative. So when you work on those problems in the future, the first thing just quickly check is the function, the f function, this part, is this continuous? If it is, you basically take that function and replace t with x. All right, how did you get that? I got something totally different. All right. We're not really finding the derivative. We're just going to use the fundamental theorem of calculus to kind of like take the f of t and then replace a t with x in this case. So how do you tell if it's continuous? It's continuous if we look at square root of t cubed plus 1. Its square root of function is always continuous as long as the function underneath the square root is positive or 0, right? So as long as this part is greater or equal to 0, and that part is greater or equal to 0 here because I'm seeing that a is greater than 0, x is greater than a, and b is greater than x. So t from a to b, since this is always positive, then t cubed plus 1, that's always going to be positive. So in this case, it's continuous. So you're not actually finding the derivative, because if you try to find the derivative, you have to integrate it and then find the derivative. But in this part, we can just use the fundamental theorem of calculus directly. The only thing you need to check is the f function, right? F of t function. If you have a rational function, so this is just a note on the side. So if, let's say you have f of x equals some function 3x over 5x plus 11x squared or something like that. This function is continuous as long as the denominator is not 0. If the denominator is equals 0, then it's not continuous. Or if you have f of x equals natural log of some function with x, I don't know, let's see, 2x squared plus 5x. For natural log, you have to make sure that the part inside the natural log is greater than 0. Another rule to check. And if you have piecewise functions, then it's get tricky. Then you have to, probably better to use either limits definition So for y prime, do we keep the integral sign on? No, so for this is a y prime, what we found at the end. Y prime is f of t, but with t replaced with x. That's what the derivative is. There's no integral anymore. All right, let me go through the second example, and then maybe that will help a little bit better to understand the theorem. So the second one says we're going to find the derivative of this integral from x to 1 of secant t dt. Right? So that's the derivative we want. So if we call this g, then we're basically looking for g prime. Right? And then this part is the f function. This is the f of t. Sort of difficult to see there. In the middle. Now, in order to find the derivative here, you have to be a little bit careful because the integral is from x to 1, it's not from 1 to x. So if we go back to the fundamental theorem of calculus, the definition is actually the integral is from a constant a to x where x is greater than a. Right? So the lower bound is a constant that we know, the upper bound is x that we don't know. So here, the lower bound is x, the upper bound is a constant we know. So we have to do something, we have to flip the integral first. So we're going to rewrite this integral. So we're looking for derivative of the integral from 1 to x. But if we flip the lower and the upper bound, remember we have to add a negative sign. So we're going to add a negative sign to that of secant t dt. So that's the very first step. You always want to make sure that the lower bound is a constant and the upper bound is the x, not the other way around. Okay. So that's just the first step. And then the next step, anyone know if secant of t is continuous or not? From 1 and going up, it is, right? Yeah, secant function is continuous. So if you don't believe me, you can graph it and check. So secant t or secant x is continuous for x greater than 1. So that means we can just use the fundamental theorem again directly. So the derivative of this integral part, if we ignore the negative sign, that will be just the given by the f function, right? But then since we have a negative sign, we have to carry the negative sign to the next step. So that's just going to be f of x, but f of t is secant t, so f of x is secant x. So this is the derivative at the end. Most of the time, you don't have to worry about the function being continuous, f of t being continuous. Most of the cases, it's continuous anyway. I probably wouldn't put any tricky questions in there for you to decide if it's continuous or not. Okay. But always check the lower bound is a constant and the upper bound is x. Any questions from those two examples? All right, the next example, similar to number 6. So next example, we have a 1 in the upper bound, and then you have x to the 6th power in the lower bound. So that's not okay, right? We always want to make sure the constant is in the lower bound. So we have to flip the sign of the integral first. So we're going to rewrite y equals, sorry, I'll let you copy down the problem first. All right. So the first thing, we're going to flip the integral signs by adding a negative in front of it. So that's integral becomes negative from 1 to x to the 6th power of cosine t dt. So this function, this integral here, just like the g we have, g of x, but we just call it y in this case. And then the f of t is cosine t. So this is the f of t that we might use. And if you remember the cosine function from 1 and then going up, cosine function is continuous. Right? It's a periodic function, continuous. But here, the second difficulty is that you have a x to the 6th power there instead of just x. Right? If we just have x there, then the problem will be simple. But here we have x to the 6th power, so it's not that simple. But what we can do is that we can use substitution. So use substitution by let u equals x to the 6th. And then I'm going to show you how to use the substitution here. So we want to find dy dx, right? But if we put a u for x to the 6th, then we have a function of u here. So we don't have a function of x. So that derivative we can write as dy du of du dx. You can kind of think about we splitting the derivative with respect to x into two parts. And this has become this part, we're just going to leave it aside. We're going to work on dy du. So that's equal to d du of this negative integral from 1 to, I'm going to substitute for x to the 6th. There's a u there, so 1 to u, cosine t dt. But then I also have a du dx at the end. So that's a first part for you when you have an upper bound that's not just x, that's something more complicated. Just use a substitution by calling that upper bound u. Now, if you look at it, this part is just kind of like a 1 to x with when we take the derivative. So this is like derivative of an integral that we can use the FTC that we used earlier. So can apply FTC1. Because that's just kind of like a d dx of integral from 1 to x cosine t dt. That's what we've seen before, right? And it's continuous. So this part, the first part, just become negative coming from the negative sign. And then we're just going to use the ft function, write f of x from that. So cosine, but not x. Here we actually have u, cosine u, because of this u here. If that's an x, if the upper bound is x, then we have cosine x. But the upper bound here is a u after substitution, so that's a cosine u. But then we also have a du dx. We have to substitute for that part. And then we also have to substitute for the u because we need a function of x. How do we get du dx? Well, we have u equals x to the 6th power we had at the beginning. So that means du dx by taking the derivative directly. So that's a 6x to the 5th power, if you remember. That's just a power rule with derivatives. We're going to use that in here so that give us negative cosine. U is equivalent to x to the 6th power, and the du dx is 6x to the 5th power. And then we just have to rewrite it, make it look nice. So that's a negative 6x to the 5th power cosine x to the 6th power inside close parentheses. Did you use a chain rule? Okay. Yes, I use a chain rule. Julie, do you have a question? So yes, I use the chain rule here. So if you, I don't know if you've seen this before, whenever we take the derivative with respect to x, we can apply chain rule there and then write it as d du of du dx. That's the chain rule part. That's what we use when we find the derivative of y with respect to x. We can write as dy du times du dx. Yes. So whenever, if we just have f of t is continuous, we just replace t with x to get the derivative of the integral function. But just be careful, make sure that the lower bound is a constant and that the upper bound is x. If the upper bound is not x, like in example 7, then you have to use substitution, and then in that process, you have to use chain rule there. So that's an extra step. So Sam, did that answer your question? So that du dx coming from the chain rule is a derivative. Any other questions about those examples? The next part of the theorem is actually a lot easier to use. Much straightforward than this one. So it's really just integrating x for t. It's really not integrating. It's basically so the theorem says if we have g function is given by the integral from a to x of f of t dt, then the derivative of g is equivalent to the f function, but replacing t with x. So this is really like like you don't actually do any integration in the process, right? You just identify the function that you integrate, f of t, right? That's a function we integrate to get g, but if we want g prime, we just take f out of that integral if f is continuous. You can also, another way to think about it, you can think about, so I'm going to write down here. So this basically says, this first part says, if f is continuous, and if g is integral is the integral function of f, then g prime equals f, basically. But then you have to make sure that the input in the g prime is x, but the f given it depends on t. So if f of t if f of t is continuous and the g is the integral function of f of t, then the derivative of g is equal to f of x. That's what the notation says. What about the lower bound? Do we still input that? No, you don't input that. So the lower bound is just to make sure that. So the reason we have the lower bound is to make sure that the function is continuous. And most of the time, the function is continuous. That will we usually work with continuous functions. But just make sure that before you apply this theorem, you need to make sure that the lower bound is a constant, the upper bound is the input. Okay, so I have one more part, which probably going to take half an hour, maybe a little bit longer. But I'll try to finish it in half an hour. But do you want to take a 10-minute break, or do you want to continue? Any preference? Keep going. Okay. All right. Okay. 2 people. All right. And if there's no objections, I guess we're just going to keep going. If you need to get water or whatever, feel free to do that. All right, the second part of fundamental theorem of calculus. This is on page 403. I hope it's going to be. So the second part says, if f is continuous on interval a to b, then if we were to integrate f from a to b, if we want to find out the value from this integral, what we could just find some function capital F. I'm going to tell you what f is, this capital F. And then we're going to, let me write this. I'm going to use a little bit different notation from the book. Hopefully it will make a little bit more sense. So if we want to integrate this integral from a to b of f of x dx, basically if we want to find the a, b, this is f of x. If we want to know this area, that's what the integral on the left side says. So this is giving me area. If I want that, I need to find some capital F of x, and I want to evaluate this. So this vertical line means evaluating from a to b. And how do we evaluate this? We just plug in b first into this capital F function minus the value we get when we plug in a into the capital F function. So that's usually we drop the middle part, just write the book use from a to b f of x dx might equals f of b minus f of a. That's a notation in the book, but I like to add the middle, like a sort of the intermediate step. So what is f of x? So where f of x, capital F of x, is the antiderivative of lowercase f of x. And such that, st means such that the derivative of f is equal to lowercase f. So basically what this says is that if you ever want to evaluate the integral from, you want to find the area, or you want to evaluate f from a to b, the integral. So what you do first is that you find antiderivative. So this is like a steps. So first step, find the antiderivative capital F of x of the lowercase f. And then the second step, you plug in b and a, find the difference to find f of b minus f of a. That's what the steps will be. If you haven't seen this, it could be like, doesn't make any sense, right? But I'm going to show you how to use this theorem in a few examples. Some of the examples will be a little bit challenging, but hopefully will make a little bit more sense. So you already know a few ways to find antiderivative, right? The power rule, that's one of them. So I'm going to use example 8 here. So example 8, we basically want to evaluate this function from 1 to 2. We want to integrate it from 1 to 2 to find the area between the curve and the x-axis. Right. So what we do, we just find the antiderivative first. So the f of x here is this part, 3 over 2 square root of x. I'm going to write as x to the half power, minus 4 over x squared. I'm going to write as 4x to the negative 2. And the e is a constant. We don't have to worry about it. Do you remember how to find the antiderivative of this function? You probably remember, right? So if we want to integrate x to the a dx, a is a constant here, just an exponent. The antiderivative will be, we're going to add 1 to the exponent, and then divide by the new exponent. That's the rule to find the antiderivative, and a plus a constant c. If you remember that. So that's what I'm going to do here. I'm going to leave the coefficients 3/2, just leave it. And I'm going to add 1 to the exponent. That gives me x to the 1/2 plus 1. I'm going to do that quickly. That's a 3/2. But then I have to divide by the new exponent. So divide by 3/2. So that's giving me the antiderivative of the first part. And then for the next part, I'm going to do the same thing, leave the negative 4, but I'm going to add 1 to the exponent. So that's x to the negative 2 plus 1, which is minus 1, x to the minus 1 power. But then I have to divide by the new exponent, negative 1. So divide by negative 1. And then the last part is e. You know what, I probably should write a few more things. But the last part is e. E is a constant, so it doesn't get involved in the antiderivative process, right? So if you integrate a constant, you just get e times x. I probably should write down this step. Let me write down a step I skipped. So f of x is equal to the antiderivative of the f of function. So basically that's equal to the integral of 3/2 x to the 1/2 minus, well, you can write dx minus integral of 4x to the negative 2 dx plus integral of e dx. That's the intermediate step that I didn't write. You're basically integrating each term using the power rule. And then the next step is just simplifying. So the next step is simplifying. So 3/2 divided by 3/2 is 1. So I get x to the 3/2 minus 4 divided by negative 1 is positive 4x to the negative 1. Can't you just use the normal antiderivative rule? Yes, that's what I did, right? So to find the antiderivative of each term, so what I did is I add 1 to the exponent of x, and then I divide by the new exponent. And then plus ex. So this is the antiderivative. That's a c, but in this part, we don't need to write the c. Let me keep the c there to show you c doesn't matter here. So that's the antiderivative. And then we need to evaluate that integral from 1 to 2. So what this says, that we're going to just find the antiderivative, which we found. So that's, I'm going to go back here. So the rule says, after we find the antiderivative, we're going to evaluate it from a to b. So I'm going to write that step. So that's equal to x to the 3/2 plus 4x to the -1 plus ex plus a c. That's the antiderivative. We're going to evaluate this antiderivative from 1 to 2. And then the next step, how do we evaluate it? We just take 2, put in there, find the number, and then we're going to put 1 in there, subtract, find the difference. So that's equal to, now I'm going to substitute 2 in for x. So that's 2 to the 3/2 minus 4, plus 4 times 2 to the -1 plus e times 2 plus a c. That's what I get when I plug in 2. And I need to subtract the value we get when we plug in 1. So that's a 1 to the 3/2 plus 4 times a 1 to the -1 plus e times 1 plus a c. Okay. Now we just calculate all the numbers that we could calculate. 2 to the 3/2, that's 2 cubed square root. So the first term here, that give me square root of 8 plus 2 times 2 to the -1, that's 4 times 2 to the -1, that's 4/2, that's a 2, plus a 2e plus a c. Then we're going to subtract all those terms. Each of them is, so the first term is 1. The second term is also, second term is not 1. So subtracting 1 plus 4 plus e plus a c. So we get square root of 8 plus 2 plus 2e plus a c minus 1 minus 4 minus e minus c. And then you can calculate and simplify, get an answer. But I want to point out that the c, so when you plug in the first number 2, you get a positive c. But when you plug in the 1, you get a c also. But because you're subtracting, so you get a negative c. So positive c, negative c give you a 0. So the c always cancels out in those steps. So there's no need to use the c when you find the antiderivative, because they cancel out in at the end. All right, I'm sure there's questions. Hold on. Go further. Let me read the final. Oh, okay. So here's a question that says, why is it ex? So e is a constant. So when you integrate e with respect to x, so the e basically comes out, becomes e times the integral of dx. Integral of 1 dx, that's just a 1 there. So integral of dx is just x. That's just a rule. It's better to remember that. So there's also a question on quizzes and exams. Okay, I'll explain that. On quizzes and exams, do you want us to simplify the big expression and we leave it as it is? Jason, I'm not sure which part you talk about.
I'm talking about like after we evaluate f of b minus f of a, can we just leave like where we, I'm kind of hard to explain.
Oh yeah, this step. Are you talking about this step that I'm on the line?
Yes, yeah, can we just leave all those numbers as they are?
No.
No, okay.
If like square root of 8, you can just write as 2 square root of 2, but the 2 and the minus 1, you have to calculate become a 1. Obviously, the 2e and the minus e, 2 minus 1 minus 4, that's a minus 3. 2e and the minus e, you can just write as a e, and then you can leave it as this if you want. But you have to try to get to the as simple as possible. So there was a question of how did you get 3 over 2x? How does it become 3/2 over itself? Okay. Yeah, so Aiden is right. So in that part, when you try to integrate 3/2 x to the half, so the first 3/2 in the numerator, that's just like the constant coefficient. I'm pulling it out, put it aside. And I'm integrating x to the half power. So we have to add 1 to the exponent and divide by the new exponent. So I add 1 to the half. So half plus 1, that will give me 3/2. That's the new exponent, but then I have to divide by the new exponent. That's why I divide by, so that's where this part comes from. It just a rule that when you integrate a power function, it's always adding 1 to the exponent and divide by the new exponent. So any other questions about this number 8? So we write as f2 equals 4, 828 times 2e. Plus 2e, right? The first two terms is 4.828, but it's addition, so it's plus 2e. You write like that, that should be okay. But if you are plugging into the calculator, it's probably better just plugging everything in the calculator, including e. So I don't know if you catch what I said. So my point is that when we find the antiderivative, there's a c at the end. We don't need to write that c because when we using fundamental theorem of calculus 2, the c always cancels out because of you subtracting a second part from the first part. There's always a c in both parts. So you don't have to write the c, just drop it in the future. All right, would you rather we plug things in a calculator and leave it as it is? No preference, whichever works for you. Sam, I don't know what f of 2 is. I think what you have is about right. All right, let's move on, shall we? Oh, you're probably hungry, so me too. Let's move on. So number 9, we're integrating from pi to 0, sine of theta d theta. It's just like an x here, right? Theta is x, but for angles, we write theta instead of x. So we want to integrate this. This part is f of x. We need to find the antiderivative of that. So f of x is equal to sine theta. So the antiderivative, sorry, f of theta. Antiderivative, capital F of theta. And if you remember that the antiderivative of sine function is not cosine, right? It's negative cosine. So recall derivative of x sine x give me cosine, but derivative of cosine x give me negative sine x. So if we have a sine x that we want to integrate, we should get a negative cosine. Just keep that in mind. So this negative sign is because of this negative sign. That's why it's negative. It's at some point, it's better just memorize that. So this is the antiderivative. So I'm going to put it in there. So when we want to find the integral from pi to 0 of this f lowercase f of theta, so we get capital, so that's a negative cosine theta. That's the antiderivative. That's a c there, but I'm dropping the c. I'm not writing the c there. So dropping the c. And then we're going to evaluate this from pi to 0. So I'm going to plug in the b first. B is the upper bound. So this is what b is. This is what a is. So we're going to plug in b first. So that get negative cosine of 0 minus, when we plug in a, which is negative cosine of pi. And the rest is about evaluating. If you remember, cosine 0 is 1. Cosine pi is negative 1. So there's a lot of negatives. Be careful, keep track of them. So we get negative of 1 minus negative of negative 1. And then you can figure out the rest. But I just want to show you the steps is that you have to find the antiderivative first and then evaluate it by plugging b and then subtract a value you get when you plug in a. Any questions about this problem? So antiderivative of sine is negative cosine. Correct. That coming from derivative of cosine is negative sine. How are we doing? Shall we move on to the next part? All right. The next function. It's we want to integrate this function 1 over x minus e to the negative x from 1 to 2. So this is the f of x function. So we're going to find the antiderivative of that. So we need to find the antiderivative of 1 over x dx first. And then we're going to find the antiderivative of e to the minus x dx. Those two parts, right? And if you recall that antiderivative of 1 over x is natural log of absolute value of x. That's the absolute value sign there. And then so let me put here. So recall d dx of natural log of x equals 1 over x. But if we find the antiderivative, we have to add an absolute value sign. And also recall that d dx of e to the x is just e to the x. But in this case, we have an e to the minus x. When we find the antiderivative of e to the, when we integrate e to the minus x, we have to be very careful So if it's e to the x, we get e to the x. So we should get e to the minus x, but because of the negative in the x part, we get negative sign in front of it. So the negative sign in this exponent, that leads to this negative sign. Julie, yes, the derivative of sine is cosine, but for the previous problem, we're not finding the derivative. We find the antiderivative. We're sort of looking for a function whose derivative give me sine. So we're looking for some function. When we find the derivative, we get sine. Yeah, so all those parts, when you find antiderivative, you kind of have to train your brain to think the sort of the reverse way. Why are there two negative with e? So the first negative is just a subtraction between the two parts of the f function, right? So that's the first negative. The second negative coming from when we integrating e to the negative x, the negative one in the exponent give us a negative sign. And that's just from experience. The more you work on those problems, the easier it gets. And then later on, when we learn what we call U substitution, that negative sign will become obvious. Right, so that's the antiderivative. So I'm going to put in the equation using the fundamental theorem of calculus. So this integral will become the antiderivative evaluated natural log of x minus become positive e to the negative x evaluated at from 1 to 2, right? That's what the antiderivative is. And then we're just going to plug in the numbers 2 and 1. So we get natural log of absolute value of 2 minus e to the negative 2 plus. And then we're going to subtract the expression we get when we substitute x with a 1. So minus natural log of absolute value of 1 plus e to the negative 1. And we just have to simplify. Absolute value of 2 is just 2, so we get natural log of 2 from the first part. You can put in the calculator if you want, or you can just leave it. Plus e to the negative 2, again, you can leave it or you can use the calculator. Minus natural log of absolute value of 1, so that's a natural log of 1. If anyone remember what natural log of 1 is, it's a very nice number. 0, right? So this part is 0, so that basically, so this term basically goes to 0. And then minus e to the negative 1 is just 1 over e. Again, you can leave it or you can put in the calculator. So we end up with natural log of 2 plus e to the negative 2 minus e to the negative 1. If you don't put it in the calculator. Question. I don't have the value. I trust you, it's 0.46. That's okay. People have different preference. Just so you know, you're going to notice that I usually don't calculate the last step. In the future, when I have a problem like this, I'm probably just going to stop here. Or maybe I'll stop at this step and then let you figure out the rest, because that's just algebraic process. So you can work on that. Exactly. Good. Anyway, move on to the next one. Otherwise, I'm not going to be able to finish. It's okay if we don't finish, but let's just try to go through as much as possible. That way you will be prepared for the homework. All right, so the next one so here we have a integral from pi over 2 to 3 pi over, pi over 4 to 3 pi over 4 of this function. So this is equivalent to f of x, but obviously theta is the independent variable. So we need to find the antiderivative. So let's call this f of theta. We need to know capital F of theta. Exactly. Anyway, how do we find the antiderivative of cosecant theta and the cotangent theta? Anyone remember? So that's the case that you're going to have to use a special trig rule. So recall that derivative of x of cosecant x is equal to negative of cosecant x cotangent x. So that's just a special rule there. But here we have a positive, but in the derivative rule we have a negative. So that means the antiderivative of this lowercase f of theta is going to be negative of cosecant x. So this, you can kind of think about, it's this negative sign going from the right side to the left side to make it positive. So that will be d dx of negative cosecant x is equal to positive cosecant x cotangent x. So the antiderivative will have a negative sign there. And then that's equal to the antiderivative, which is negative cosecant x. In this case, I'm going to, cosecant theta. Evaluate it from pi over 4 to 3 pi over 4. And then that's equal to negative cosecant of 3 pi over 4 minus negative cosecant of pi over 4. And then the rest is about, if you remember the trig identity well, you can figure it out. If you didn't remember it, you can use a calculator. 3 pi. So that's a negative 1 over sine of 3 pi over 4 minus plus 1 over sine pi over 4. Right? And then 3 pi over 4 and pi over 4, they're the same. So that's a negative 1 over root 2 over 2, 3 pi, yeah, root 2 over 2 minus 1 over root, plus 1 over root 2 over 2. And then you end up with a 0, I believe. Double check this calculation. I'm not sure if it's 0. It looks like a 0 to me. But any questions about the very first step to find the, if it's like a really infinitely small, that means it's just calculation error. If it's like I give you like 10 to the negative 6 or 10 to the negative 9, it's it means it's 0. Okay, good. Excellent. So the very first step is just finding the antiderivative. That's a key step. And then the next step is about plugging those values in there into the antiderivative and find the difference. That's also an important step. The rest is really not the important parts. It's important, but not that important. Okay. Shall we move on? I get 2 more examples. All right then. So the next function is 1 over x squared plus 1. This is a special function. I'm actually going to ask you to remember it. It's, so that if this is f of x, so f of x equals 1 over x squared plus 1, then the antiderivative f of x is equal to inverse tangent of x. There's no other way, just remember it. So we're going to use it, put the antiderivative in there. So this integral using the FTC2, we get the antiderivative inverse tangent of x evaluated from 0 to 1. And then that's equal to inverse tangent of 1 minus inverse tangent of 0. I don't know how comfortable you are with inverse trigonometry. Inverse tangent of 1 basically asking you tangent of what angle, give me 1. So that's what this first part is. Tangent of what angle will give me 1. And then if you remember, it's 45 degrees. But we're not going to use 45 degrees. We're going to use pi over 4 here. And then the second part is asking tangent of what angle, give me 0. And then that's tangent of 0. So you just get pi over 4. But like I said, the first two steps to find the antiderivative and also to plug in those two values, those are the important steps. If you get the first two steps right, and then you made a small error at the end when you evaluate those two parts, that's no big deal. Of course, I'm going to take some points off, but not the worst part. And just use your calculator if you want to. But if I do, let's just say I give you a problem like this on a quiz, right? Make sure you show the steps. Don't just say, oh, the answer is pi over 4 at the end. You have to show the steps. Otherwise, I don't know if you do everything in your head or if you just saw it in a previous example. Make sure you show the steps. All right, any questions about this one? So maybe just remember this special antiderivative. If we wrote the answer at 45, no, I wouldn't take points off, but just keep in mind that actually from now on, like if you were to take calculus 3 or differential equations or linear algebra in the future, very rarely we're going to use degrees for angles. We always use radians. So it's better to get comfortable with radians. This last one. Oh, which last one? 12. So I'm currently taking differential. Oh, okay. That's good. Julie, is it number 12 that's confusing? Yeah. So it is confusing, right? But it's really just a special function. So the f of x, lower f of x, 1 over x squared plus 1. The antiderivative is just a special function, inverse tangent of x. It's better just to remember that. And then plug in the values 1 and a 0. If you have a calculator, it's probably a lot easier. But it's use trig identity that you learned in the past. Okay, if you have more questions, I can send you some practice problems. All right, let me finish this last part. So this last part, this is actually the most confusing problem. So here, this is the function. I'm not sure. If you ever want to take differential equations, you need to know calculus 2 really well. Like that's sort of the foundation for differential equations. of course, calculus 1 as well, right? So anyway, let me finish this and I'll let you go. So f of x is equal to 5x minus 2. So I'm going to rewrite this as 5x over 5 squared. And the benefit of doing this is that I have 5 squared in the denominator. That's just 1 over 25 times 5x. This part is just a constant coefficient. I don't have to worry about it in the process of integrating. So let's just focus on the 5x part. So the antiderivative is equal to 1 over 25 integrating 5 to the x power dx. So we just need to find this. So what is this antiderivative? It looks very similar to e to the x, right? If we have e to the x, so recall, if we integrate, if we have derivative of e to the x, we get e to the x. But if we have a derivative of a to the x, we get a to the x multiplied by natural log of a, right? Natural log of a is a constant. So, but here, I just have 5 to the x. I don't have the natural log. So what we can do is we can divide by natural log on both sides. So d dx of ax divided by a to the power of x divided by natural log of a, that will just give me a to the x. It comes from here. So this is what's useful to us. When we're integrating a to the x, we should get a. So let me write down this. If we're integrating a to the x with respect to x, for any a, constant a, we should get a to the x divided by natural log of a. You can remember this integration rule there. So we're going to use it in this part. How did you get 1 over 25x? So that come from rewriting 5x minus 2. Rewrite it as 5 to the x divided by 5 squared. And then 5 squared is just 25. So I put it in front of the 5 to the x term. So that's how I get 1 over 25 times 5 to the x power. So after I've done this, so the antiderivative is just 1 over 25, 5 to the x divided by natural log of 5. So that's what this, so this integral gives me this part. And now I'm just going to rewrite the integral using the antiderivative. So if we evaluating from -2 to 0 of this function, so that becomes antiderivative 1 over 25, 5 to the x over natural log of 5, evaluated from -2 to 0. So we're going to plug in 0 in there and plug in -2. So we get 1 over 25, put 0 in there. So we get 5 to the 0 over natural log of 5 minus 1 over 25, and then 5 to the -2 over natural log of 5. And you can calculate a few things, not a lot, you can simplify. You can factor out 1 over 25 if you like, and then factor out 1 over natural log of 5, and end up to be 5 to the 0 minus 5 to the -2, which you can calculate is 1 minus 1 over 25. So you get 24 over 25. So basically you get 24 natural log of 5, and then 24 over 25. So 24 over 25 squared, 625, and then natural log of 5. You don't have to leave your answer like this if you want to put in the calculator from So I'll use calc reading here. So it's okay to use a calculator after you write down this expression. So again, I recommend that you memorize this integration rule. So integral of a to the x dx is always going to be a to the x over natural log of a. That comes from the derivative of a to the x. All right, we have 1 minute left. Obviously, I'm going to stick around a little bit longer just in case if you have questions. Any questions about this problem or any other things that you didn't get a chance to ask? For those of you that I didn't see your face today and I didn't see your face on the profile picture, please update your profile picture in there. You know, that way I'll be a lot happier. All right. If you don't have any questions, good to see everyone here. I'll see you guys on Wednesday. Take care.
Thank you.
Thank you. Bye.
Thank you.
Take care. Bye.
Thank you.
Thank you. Bye.
Thank you.
Thank you, everyone. Take care, everyone.